If you are joining us for this deep dive, you probably love uncovering those little aha moments in completely unexpected places.
Oh, absolutely. The best insights usually hide in the most ordinary things.
Right. And today's source material delivers exactly that. It's a micro mystery, really. But before we get into it, I want to talk about how we usually look at the results of a test.
Okay, lay it on me.
So there is this deeply ingrained expectation we all have of straightforward causality. Like, think about cars for a second.
Sure.
If you have two vehicles and they both get the exact same terrible gas mileage, the natural assumption is, well, both of them just have horribly inefficient engines, right?
Right, because we see the identical output on their dashboard, an empty tank, and our brains automatically trace that back to a single identical mechanical failure.
Exactly.
We rely on that cognitive shortcut constantly.
Yeah.
The human brain loves efficiency, so it assumes the internal mechanism is the same because the final metric is the same. I mean, it saves us the trouble of investigating every single anomaly from scratch.
Yeah, but what if one car actually has a poorly tuned engine and the other car is in perfect working order, but it happens to have a massive puncture in the gas tank?
Well, then you've got a completely different situation on your hands.
Right. The data on your dashboard reads identically in both scenarios, but the underlying reality of what went wrong is entirely different.
Totally different.
And if you approach that second car and try to fix it by, like, rebuilding the engine, you are setting yourself up for endless frustration. You'll put it all back together, fill it up, and watch it fail all over again.
Because you are attempting to solve a structural problem with a mechanical solution. The data was accurate, the car was out of gas, but your interpretation of that data was blinded by a hidden variable.
And that is the perfect setup for today, because today's source material is a brilliant micro mystery that perfectly illustrates this trap.
It really does. It's a fantastic example.
We are looking at a specific entry from a serialized journal called Notes on Gardening. This was published on April 29th, 2026 by a gardener named Ang.
Yes, and we should note, we are looking at part 880 of these notes.
Part 880. That's just wild to me.
It is. What's fascinating here is that reaching part 880 implies a level of dedication where you are no longer just making casual weekend observations.
Right. You're not just throwing some seeds in the dirt and hoping for the best.
Exactly. You are establishing baselines, tracking variables, and logging data over a really long period. It tells us we are dealing with a deeply methodical environment.
Our goal today isn't just to talk about gardening, though. We are exploring a backyard experiment involving basil seedlings, moisture retention, and 3 different types of containers.
Yes, the container test.
We want to unpack how a simple observation about watering plants perfectly illustrates the scientific method and, like you said, the danger of hidden variables. I just love when everyday people turn their backyards into these informal laboratories.
Oh, it's the absolute best kind of science.
Okay, let's unpack this. Before getting into the surprising results, we need to establish the specific parameters of Ang's experiment. So you, the listener, understand the playing field.
Right, we need to set the scene.
So Ang is transplanting basil seedlings and decides to reuse 3 different types of containers. We have EPS foam cups. So that's your classic lightweight expanded polystyrene.
Yep, the standard foam cup.
Then we have recycled cardboard cups. And finally, standard plastic gardening pots. It's kind of like a DIY science fair project or a stress test for structural engineering, but for plants.
That's a great way to put it.
But why is moisture retention such a crucial metric to track in the first place? Like, why does it matter so much at this stage?
Well, seedlings are in a highly vulnerable transitional phase of their life cycle. Their root systems haven't fully established themselves in the new soil yet.
So they're kind of fragile.
Incredibly fragile,
Yeah.
making their immediate physical environment critical to their survival. Hydration at this stage, it dictates the structural stability of the entire plant.
Right, because if the soil dries out too rapidly, the seedling is thrown into severe osmotic stress.
Exactly. It doesn't have a deep, mature root network to hunt down remaining moisture in the dirt, so it just wilts.
It just gives up.
Yeah, pretty much. But if the soil stays consistently moist, those fragile young roots can safely spread and anchor themselves.
So by choosing 3 incredibly different material compositions, foam, cardboard, and plastic Ang, inadvertently creates this rigorous comparative test.
Which is brilliant, honestly. Reusing everyday items creates a perfect comparative test for material properties and their relationship to hydration.
The setup isolates those material properties. It is essentially a DIY stress test for
Yes,
microenvironments.
you have three different structural matrices trying to perform the exact same job.
Keeping a small pocket of soil consistently damp.
Right. And the data from Eng's journal reveals a stark divergence in performance.
With the competitor's setup, we naturally have to look at the extreme ends of the data, the best performer and, well, the worst.
The clear champion and the spectacular failure.
Exactly. So the EPS foam cups are the ultimate winner for moisture retention. According to the notes, they perform so exceptionally well that Eng realizes the basil in these foam cups doesn't even need to be watered every single day.
Which is huge for a seedling. The moisture is effectively locked into the soil for extended periods.
On the flip side, the absolute worst performers are the recycled cardboard cups.
Oh yeah, they failed completely.
Eng observes that the water just vanishes. The notes specifically mention that even though these cardboard cups have 0 drainage holes punched in the bottom, they lose hydration rapidly.
And Eng deduces that the water is somehow evaporating from all sides of the cardboard cup.
Which forces us to look at the microscopic structure of the materials, right?
Yes. Cardboard is essentially a highly porous matrix of compressed paper fibers. The physics at play here center on capillary action.
Capillary action, right.
So when moisture in the potting soil makes contact with the inner wall of the cardboard cup, the paper fibers physically absorb that water.
They act like tiny conduits.
Exactly.
Ah.
Wicking the moisture outward, drawing it straight through the wall of the cup to the exterior surface.
Here's where it gets really interesting, at least to me. It behaves almost exactly like a damp sponge left out on a kitchen counter.
Oh, that's a perfect analogy.
Right. The sponge isn't just holding water, it is constantly breathing out that moisture into the surrounding air.
Because once the water reaches the outside layer of the cardboard, it is fully exposed to the ambient air and it just begins to evaporate.
And because the cup is cylindrical,
It is losing water from 360 degrees of its own structure. It doesn't merely lose water from the small exposed circle of topsoil at the surface.
the entire container acts as an active evaporation engine.
Yes, the material itself is constantly pulling water away from the seedling's roots and feeding it directly to the atmosphere.
It is maximizing the surface area exposed to the air. Meanwhile, the EPS foam cup acts like a completely sealed thermos, locking the hydration in.
Because expanded polystyrene is basically a matrix of trapped air bubbles encased in a non-porous polymer.
So no capillary action.
None whatsoever. It does not absorb water, and it certainly does not wick moisture from its interior to its exterior. It forms a hard, intangible barrier.
Meaning the only place the soil can lose moisture in the foam cup is from that tiny surface area of dirt exposed at the very top.
Right. The walls of the cup are contributing absolutely nothing to the evaporation process.
The logic driving these results is incredibly clean. We are looking at a beautiful scientific binary that allows us to build a predictive model.
A very simple one, too.
Yeah. Porous paper absorbs water, wicks it, and breathes it out to the air, resulting in dry soil. Non-porous foam blocks water, traps it inside, and maintains hydration.
Based on that binary, you can theoretically predict the performance of any other material you introduce to the test.
You simply have to ask, is the material porous or is it non-porous?
Which brings the standard plastic pot into the spotlight?
Yes, the anomaly. If we apply our predictive model, standard plastic should logically act like the foam. I mean, it should be the exact equal.
It really should. Plastic is the ultimate non-porous material. It is the bedrock of modern waterproofing.
Right, plastic does not wick moisture. It has no capillary action.
And it forms a completely impermeable barrier between the wet soil and the dry ambient air outside the pot.
Yet, Eng's notes reveal an unexpected finding that completely shatters the model. The standard plastic gardening container performs surprisingly poorly.
Shockingly poorly.
It actually ties for last place, leaving the soil just as dry as the highly porous cardboard.
This creates an immediate moment of cognitive dissonance for the gardener. You have a material that is universally understood to be waterproof, completely failing a basic water retention test.
Wait, I have to actively push back on this finding to bit of a mystery here because this defies basic logic. Plastic is completely waterproof.
It is.
Human beings use plastic to build boats. We store caustic liquid chemicals in plastic jugs for decades without losing a single drop.
That's entirely true.
How can a solid waterproof material tie for last place with a leaky, breathing piece of cardboard? It feels structurally impossible.
And that exact sense of impossibility is what makes this journal entry so compelling to analyze. If we connect this to the bigger picture, This perfectly captures a classic aha moment in data analysis.
When waterproof plastic mimics the behavior of porous paper.
Exactly. When experimental data directly contradicts established physical laws or our basic assumptions about material properties, it means the mental model driving the experiment is broken.
You stare at the dry soil, and for a moment, you think the universe has simply stopped working correctly.
But really, it just forces you to pause, stop looking at the end results, and start hunting for a hidden variable you missed.
Because the core assumption going into Eng's observation was that material composition was the sole factor dictating moisture loss.
Right, the entire framework of the test was built around comparing polystyrene against paper against plastic.
So Eng is looking at a cardboard cup and a plastic pot. Two wildly different materials producing the exact same frustrating result, which is dry basil.
To solve the mystery of the waterproof plastic acting like porous cardboard, Eng had to abandon material science entirely.
The chemical makeup of the containers had just become a massive distraction.
It really had. The answer didn't lie in the polymers or the paper fibers. It lived in the physical geometry of the vessels.
The epiphany hits. To solve this, Eng had to look past the material science. What was the realization?
The mystery is solved by an incredibly simple, almost invisible structural detail. The plastic pots simply have more drainage holes punched into their base.
More drainage holes, that's it.
That is the big reveal. The plastic wasn't evaporating the water into the air. It was succumbing to gravity. It was literally just letting all the excess hydration fall out the bottom of the pot.
So, what does this all mean? Let's bring it all together. It is like comparing a bucket with a giant hole punched in the bottom to a bucket made entirely of fine wire mesh.
Oh, I love that analogy.
Right. If you fill them both with water and walk away, they will both be completely empty when you come back an hour later. They are completely different structural problems, but they both leave you with an empty bucket.
Yes. The mesh bucket loses water because of its material nature. It is permeable everywhere, much like the cardboard cup.
Breathing it out.
Exactly.
Yeah.
But the solid bucket loses water because of a specific physical geometry, the hole in its floor, which mimics the plastic pot.
But the final data point, the empty bucket, or in Eng's case, the dry soil, is completely identical.
It really shows Eng's phenomenal critical thinking to recognize this distinction. It is incredibly easy to mistake a structural variable, like the amount of drainage holes, for a material property, like the evaporation rate.
Especially if you aren't paying close attention.
Right, if you aren't actively checking your own assumptions. It's a perfect example of how multiple distinct mechanisms like evaporation versus physical drainage can yield the exact same empirical data point.
The brain just latches on to the most obvious visual contrast in the lineup.
It's a textbook example of observer bias.
We look at the foam, the paper, and the plastic and think, well, these three things are visibly made of different substances, therefore any difference in the result must be caused by what they're made of.
Because texture and substance are the most immediate sensory inputs we process. Overcoming that bias requires stepping back and recognizing that entirely distinct physical mechanisms can yield the same result.
Evaporation through a porous wall and gravitational drainage through a floor hole both leave you with thirsty basil.
And if you don't account for the drainage holes, you will spend an eternity trying to calculate how a piece of solid plastic is managing to evaporate water at the speed of porous paper.
You'll invent all these complex theories.
You really will. You will invent increasingly complex theories to explain a phenomenon that is actually just gravity doing its job.
So why does a story about basil seedlings matter for you listening to this right now? Whether you are prepping for a meeting, catching up on reading, or analyzing complex market data.
It is a masterclass in questioning the why behind everyday phenomena.
Because data without context is inherently deceptive. When a system doesn't behave the way its components dictate it should, there's almost always a hidden variable waiting to be found.
You have to look past the obvious surface-level differences and quite literally check the bottom of the pot.
Let's briefly recap the mechanics we have explored today. EPS foam insulates, locking the moisture in because of its closed cell structure.
Right. No evaporation, no drainage.
Cardboard breathes because its porous fibers wick water and act as an evaporation engine.
And standard plastic drains. It will entirely betray its own waterproof nature if you forget to count the holes.
The variables we forget to measure are almost always the ones driving the actual outcome, which leaves a rather provocative puzzle for you to mull over as we wrap up this deep dive.
A final puzzle. I like it.
If these seemingly simple plant containers act as highly engineered microclimates defined by material and drainage, there are likely other invisible forces at play that Ang hasn't even logged yet.
Like what?
Well, we have completely ignored the visual properties of the containers. Consider the color.
Oh, wow. I didn't think about that.
Right. Imagine a dark, heavy plastic pot versus a bright white EPS foam cup. How might the color of those containers be secretly affecting the soil temperature as they sit out under the sun?
That's a huge point. A dark pot absorbing thermal radiation would radically change the evaporation rate of the soil inside, and that acts entirely independently of both the drainage holes and the material porosity.
It introduces thermodynamics into an experiment that was only trying to measure hydration. Could that be a third invisible variable driving this entire evaporation mystery?
It makes you wonder how many other hidden variables are sitting in plain sight, quietly dictating the results we see in our own work.
It really does. So the next time you encounter a set of data that completely defies logic, think of Ang's basil. Before you start trying to rebuild the engine, take a moment to check the gas tank for holes.